Okay, let's start. Good afternoon, everybody. Welcome to the ISSP Colloquium Dynamical. I'm an organizer of あれ大丈夫かぶってるすいません。Okay, I'm an organizer of this colloquium, Tao Nakajima from Neutron Science Laboratory of ISSP. Thank you very much for attending for this colloquium. I'm happy to see many people here, and also now we have more than 90 audience, 97, probably 100 audience online in the Zoom session. Today we have a great guest, Professor Syk Sensei from Harvard University. We are very happy to have his talk in this colloquium. And also, I'd like to thank Oshikawa Sensei for arranging this colloquium. Oshikawa Sensei kindly prepared an introduction of Syk Sensei. You may have seen the introduction on this poster of this colloquium today. So let me share English translation. So Professor Syk has contributed to the construction of modern quantum condensed matter physics by proposing spin-rigid phases and reconfined quantum criticality in quantum spin systems. He introduced the Syk model to describe spin-rigid in random systems. And this model turned out to be closely related to the theory of quantum gravity. And Syk model has also been actively studied as a central problem in a wide range of fields, including quantum physics, quantum gravity, particle theory, and quantum information. So in this symposium, these exciting developments will be explained for a wide range of audience, including non-specialists. So the title of his talk is When Nature Entangles Millions of Particles from Quantum Materials to Black Holes. Please start.
Okay, mic is working. Yes, thank you very much for the kind introduction and all the wonderful hospitality here in Tokyo. All right, so I'm going to talk about how entanglement appears in many naturally in systems around us. My research was motivated in particular by studies of the high temperature superconductors. But somewhat surprisingly, it has also found connections in studies of quantum black holes, as I hope to make clear in a presentation today. So let me begin rather historically and just remind you of some very basic facts of statistical mechanics, in particular the important contributions of Boltzmann. So Boltzmann was thinking mostly about dilute gases and their thermodynamic properties. And one of his first fundamental contributions was the statistical interpretation of entropy. So entropy had been viewed as some quantity that appears in thermodynamics, but Boltzmann was the first to make a microscopic connection and identify entropy as the logarithm of W, where W is the number of possible microstates available to a system. Now, this was for a classical system, but Boltzmann result also applies for quantum systems. And there we can relate the entropy at energy E to the density of quantum states, the many-body states of any quantum systems. So this is a rather important microscopic connection to a macroscopic thermodynamic quantity. The other important contribution by Boltzmann, made a few years later, is the famous Boltzmann equation. And this really laid the foundation of modern statistical mechanics, and really is the foundation of almost everything we do in even in condensed matter physics, even today. So the equation is expressed in terms of the distribution function Fp of some particles. In this case, he was thinking about classical particles. And the left-hand side is essentially an expression of Newton's laws written in this form, where F is the force on each particle. Boltzmann innovation was the right-hand term, which is the collision term. It describes how the distribution function changes due to collisions. And his major assumption, which even today in some sense is unproven, is what we would call molecular chaos. That successive collisions are statistically independent. And this meant that you could write the collision term as simply the proportion of the product of the probabilities of occupying momentum P and momentum P1 for this sort of collision. And there's a second term which represents the time reversed collision. And T is some probability, T squared is the probability that the collision happens. So with this equation, he was able to show lots of very interesting things, including the second law of thermodynamics, and also compute dynamical properties, which involve dissipation like viscosity. So this is really a very fundamental and important contribution. Okay. But underlying it was this assumption of just independent collisions following each other. And you don't have to worry about the fact that this particle just collided with this particle and worrying about its future. Now, the remarkable thing is that Boltzmann's equation applies even without change, with only very small changes, even for a dense gas, but a dense quantum gas. So if you take a dense quantum gas, as might be found in a metal where you have a dense gas of electrons, you get essentially the same equation. The only change, as you can see here, are these 1 minus F factors. And this is simply the Pauli's exclusion principle for fermions, telling you that the final states of the collisions should be empty. But beyond this, it's essentially the original form as suggested by Boltzmann. And this is indeed the foundation of the modern theory of metals. So if you want to describe, for example, how current flows in copper, you just solve Boltzmann's equation by treating the particles as nearly independent of each other. And if you solve Boltzmann equation, you'll find that the electron-electron scattering time diverges as 1 over temperature squared as temperature goes to 0. And one of the consequences of resistivity increases as T squared. So now you can ask, well, when does Boltzmann break down? When does this description in terms of these distribution function of these particles, independent particles with independent collisions, when does it break down? Well, certainly if the collisions happen really often, and so often that you couldn't even identify the particles clearly, this couldn't work. And so with that kind of reasoning, you then conclude that at a temperature T, if your scattering times become shorter than Planck's constant divided by temperature, then this should break down. And we can't have any system where this scattering time is shorter than this fundamental Planckian time, as it's often called. And if it's much longer than this, then perhaps there's a hope of this independent particle description to hold. Okay, so this paradigm has been with us for a long time. I would say up until 1980, there were no problems with it. Everything that was observed could be really explained very well by this Boltzmann picture extended by Landau and applied to numerous electronic flow in numerous materials. So, of course, in 1987, we had the great discovery of high temperature superconductivity in yttrium, barium, copper oxide. And pretty soon it was discovered that there was a regime where the Boltzmann approach doesn't work, and even at low temperatures. And this is often called the strange metal now. And this strange metal has the property, for example, that if you measure the resistance as a function of temperature, rather than going as T squared, it's very linear in T. This is some observations in lanthanum, strontium, copper oxide. And on the right-hand side is a modern material, the twisted bilag graphene, where again you have resistivity linear in T. Now, this is not the only disagreement with Boltzmann theory, this temperature dependence being totally off. There are many others. In particular, I also show this recent data by Brad Ramshaw's group. They looked here at what's called angle-dependent magnetoresistance. I won't go into it at all, but you have to take my word for it that from these measurements, they could estimate this collision time that I talked about. And there was an isotropic component of the electron scattering in this material, which gave a collision time h bar over tau, which was a linear function of temperature. And they could then read off the coefficient, and lo and behold, it was very close to unity. So this material, it seems, is right at the bound of where a Boltzmann equation could apply. And it's kind of mysterious that the scattering time just depends on kT and not on any underlying energy scale determining interactions between the particles. Okay. So that's really the basic puzzle that's been with us since the late 80s. It seems like you have metals, and many more have been discovered since then, where the Boltzmann-Landau quasi-particle description doesn't apply. And this must mean that the central assumption that successive collisions are independent must break down. So we have to not only look at the probability of the collisions being correlated, but also look quantum mechanically at successive collisions interfering with each other. That you can't just add probabilities, you have to look at the amplitudes of successive collisions. And today we would say this means really you have to worry about the entanglement of the particles. Okay, so that leads me to what's now called the SYK model, which turns out to be solvable description, somewhat artificial description, admittedly, but at least a solvable description of some many-body system where we can prove that there isn't any Boltzmann-Landau description. There are no quasi-particles, and then we come up with what happens, and I'll describe that to you in a little bit. So just to introduce things in perhaps too simple a manner, the essence here is really many-particle entanglement, and the idea of entanglement goes back to Einstein, Podolsky, and Rosen in 1935, where they talk about a thought experiment where you imagine you have two particles, one with spin up and one with spin down, and their state is this particular state, up, down, minus, down, up. And they propose that if you were able to separate these particles far away without disturbing their spin, they would still be entangled. They would still be in this superposition state. And this led to the apparent contradiction that if you measured a particle here and found it to be down, then at that instant, there was what Einstein, in fact, called spooky action at a distance in a letter to Max Born in 1947. And the spooky action at distance will force the state of the particle far away to be the same as the particle that you measured over here. So if you measured down, it would be up, and if you measured up, it would be down. Of course, we understand this very well today. Well, I wouldn't say very well, but we know this is true. But we don't like the word spooky action at a distance because really there's nothing going from one particle to the other. And the theory is very local. There's no action at a distance. It's causal and it's local. What's not local is the idea of a quantum state. The quantum state shared by these particles is not a local concept. It's something that developed when they interact locally in the past, but it doesn't sit here nor there. Okay, anyway. So now we want to go from two-particle entanglement, which we understand extremely well, to many-particle entanglement. And here I just want to refer to, where an example of entanglement that actually appeared in 1870 somewhere by Kekulé, who proposed a theory of the benzene molecule. So if you focus on 6 electrons on the ring of carbon, they form these kind of entangled pairs where these 2 electrons entangle and these are entangled and that's entangled. The way we say it today, Kekulé talked about double bonds between carbon, and the actual state is a superposition where it's neither one nor the other. And so this, in today's interpretation, is a state of 6 entangled particles. And I just looked up on Wikipedia and I learned about Kekulé's spooky dream, where he said that he discovered the ring shape of the molecule after having a daydream of a snake sneezing its own tail. So then I decided that that I should also have a dream. So this is my spooky dream, and it's based on the ancient Indian game of snakes and ladders. You may have seen it in England. It's called Chutes and Ladders. I think the English people didn't like snakes. But in this game, if you fall on a square where there's a snake, you're bitten by the snake and you go down there. And so there are snakes everywhere, and you can, in principle, fall short distances or large distances. And now just replace snakes by entanglement, and you have the SYK model. Okay, so what is the SYK model? It's a solvable model of multi-particle entanglement where you can account for quantum interference between successive collisions. And satisfyingly, that leads to a metallic state in which there are no particle-like excitations. So let me describe the model. So at this point, this is just a toy model, and we'll talk about its connection to something in nature soon enough. Everything okay? Oops. Should I okay, how long was the mid? Do I have to go back or you okay. Oh, something was there. I just saw it. Oops. Oh, this here, is it me? Oh. No, I may have hit this wire. No, the wire there on the wall. Yeah, that connection is a little bit. You are sharing the screen. Yeah, but this. Yeah, video. Okay. All right, should I start? All right, so yeah, so I'm going to now describe the SYK model. So imagine you have a bunch of quantum states that can be occupied singly by fermions. So you have just labeled these states as 1 through 19. They could be any label, not necessarily the position. And then you place a few electrons in these states. They obey the exclusion principle. And let me just ignore spin for now. So then these purple sites represents occupied states, and then there are empty states around. So now these electrons are going to move around. They're going to quantum mechanically want to tunnel from place to place. And the basic rule of this model is that they only can move in pairs. So for example, the electrons from site 11 and 12 can go to site 5 and 14. And this process has some amplitude. So this is a complex number which represents the amplitude for this process to happen. And so that if it happens, this is the state you go to, and so on. So you just pick any two sites which are occupied, in this case 4 and 5, and you go to 11 and 18, and there's some other amplitude. So for every such allowed process, you have an amplitude. That's what defines the Hamiltonian of the system. And these processes can all happen, and in fact, they're all happening in parallel. So in principle, given a set of complex numbers, there are roughly n to the 4 complex numbers, and you have n sites, you want to figure out what the many-body state looks like. So that's very rapidly becomes a very difficult problem to solve, because the total number of states is exponential in n. And really, it's hopeless for any given set of numbers to solve them. But the remarkable thing is that if you assume that all of these numbers are statistically independent numbers with the same distribution, then you can solve it, at least in the limit of large n. So really, that's all there is to it. So here's a more technical version. In the second quantized notation, alpha, beta, gamma, delta represent these n positions, and there's an amplitude for going from site alpha, gamma, delta to site to alpha, beta. In this version of the model, we conserve the total number of electrons, Q, and the density, which is Q really, it should be between 0 and 1. Okay, so it's convenient to take them to have 0 mean. And you can take any distribution you want as long as they're statistically independent. Okay, so this model can be solved in the large n limit, and we solved, quite a few of its properties already in 1993, and through it was a slightly different model, and this particular model, closely related one, was introduced by Kitev in 2015, and now the last 4 or 5 years, we've understood much more about its properties, including the corrections at finite n, as I'll now describe. Okay, so let me just present some numerical results and their analytical interpretation. Later on, I'll give you some idea of how they were obtained. Okay, so the things we would like to compute are, say, the partition function, from which you get the free energy and the entropy, and then you can invert these formulas to get the density of states. So this is the many-body density of states of all the eigenstates of this Hamiltonian. Now, if you really want the density of states as a series of delta functions, that's hopeless. You would need to know all the exponentially many energy eigenstates exactly. But even though the density of states is hopeless to determine, once you take the Laplace transform, the free energy actually can be determined very accurately, and will turn out to be independent of the precise energies that you have. Okay, or if you want to determine the density of states, you have to do a little bit of coarse graining. And we'll see how that works. Okay, so one of the first results which that I want to talk about was obtained in this work with George and Parcollet 20 years ago, is quite a surprising result, which I will try to help explain its meaning in a minute. So one of the things that became clear from the early work that this system looks sort of like a conformal field theory. And if you know a little about conformal field theory, then you know that in d spatial dimensions, as the temperature vanishes, the conformal field theory has entropy density T to the D. Now here, there's no dimensionality. It's because any electron can hop anywhere. It's more like a 0 to +1 dimensional conformal field theory. So T to the 0 is just a constant. And so you conclude that the ratio of the entropy density, S divided by the number of sites, where you take the n goes to infinity limit before you take the limit t goes to 0, is a number. And in fact, it's a universal number, independent of all the details of the model. And we, in fact, computed this number, and this is, well, okay, this is what it is. So what does this mean? This seems initially to be a violation of the third law of thermodynamics, but it isn't, because the third law of thermodynamics is really the opposite order of limits. So in this order of limit, what does this imply? Well, I mean, if I just put S equals NS naught and use these formulae, then you would conclude that naively that there's a degeneracy of the ground state, and the degeneracy is e to the NS naught. But this conclusion is actually relies on taking the other orders of limit. We'll see that this is not correct. There is no degeneracy of the ground state. So what's going on? Well, for that, you need to really know something about the entropy at finite temperature. And so if you compute it, you find that there's a linear correction to the entropy. It's S naught plus gamma T. Now you plug this in here and just invert it. This is just the same as going from the canonical to the microcanonical ensemble. And then you find that the density of is now a function of energy. It's e to the ns naught plus square root of 2n gamma e, when the energy is extensive. And gamma is the same number gamma over here. Okay, so now you have a density of states is exponentially large, which makes sense. But is it really exponentially large as the energy goes to 0, which is what this formula would suggest? Because if it's really exponentially large at the ground state, then you have a huge degeneracy, which seems highly implausible for a system with random couplings. Okay, so you just go to the computer and you look at all the energy eigenstates. So this is a plot of all the energy eigenstates with various levels of precision. So if you look at all of them, this is for a system of size 16 or something like that. You get this smooth looking curve, and you blow it up, well, and bin the states. This is what they look like. And this is what they look like at the very bottom. So this behavior here is consistent with this prediction. And then if you look at very low energy, you find that, yeah, it seems consistent with the fact that this formula still holds, and the density of states down here is exponentially small. So really, that's what's surprising about this system. So the energy level spacing is exponentially small, the density of states is exponentially large. So what's surprising here is that although for any thermodynamic system, when the energy is extensive, the entropy is extensive, and therefore the density of states is exponentially large. And that seems to hold all the way down to the ground state. Okay, so now we really want to understand the behavior here a bit better. And to do that, we have to go beyond this large N theory. And I'm just going to outline very briefly how that's done. So forgive me for the somewhat technical discussion that follows. So the way this works is you take the Hamiltonian, you average over all the couplings, and after some manipulations, you can rewrite it exactly as this path integral for the average partition function is an integral over two fields we call G and sigma, and which are functions of 2 times, and there's some action. When you take the saddle point, you get these Schwinger-Dyson equation. These were obtained by us in '93, and you can solve them, put them back into the action, and get the results I've already mentioned. But if you want to really go beyond the saddle point, you have to look at fluctuations of this path integral. And in general, that's an essentially impossible task. Nobody knows how to do that. But turns out to be a beautiful trick for understanding its behavior at low energies. And that trick relies on the fact that if you look at this action and you drop this particular time derivative term, then this action has a huge symmetry. It's a symmetry of time parameterizations, tau going to sigma, and also an emergent gauge symmetry. So the action doesn't change at all when you do this time parameterization, provided you can ignore this term. But you can't ignore this term, so you then have to figure out how to account for this term, but under these transformations. So the way you do that is you take your path integral and you only integrate over a very small set of paths. So G star is the saddle point. You only integrate over all time reparameterizations of the saddle point. So your integral over G and sigma, which are functions of tau 1 and tau 2, now becomes an integral only over f of tau, and similarly for the gauge transformation. Okay. And then you can use some general symmetry arguments to determine this. I won't write it down. It's the short chain action. And amazingly, shown by Witten and Stanford, this whole path integral can be done exactly. Okay, so with that interlude, let me just tell you what you find from there. So from that approach and this integral over time reparameterizations, you find the corrections to the entropy, and therefore by an inverse Laplace transform to the density of states. And this is what you get. You get a correction here, which is minus 3/2 log of 1 over temperature. And then if you invert that, that translates into this sinh square root of 2n gamma e. There's also, so this is the basic result for the density of states at small energies. And this was obtained, the work of many people. This was first obtained, that exponentially large factor was first obtained by us. This factor by Kotler et al. And this prefactor here, that's the most subtle, which I won't say anything about. Okay, so you put it all together and now you can understand what's going on here. This is the overall density of states. When your energy is extensive, then you get the result we guessed at very simply from converting the linear temperature dependence to this energy dependence. And then when you go down to very low energies, there is still an exponentially large factor. And this sinh becomes a square root of E. So the density does vanish, but the coefficient is exponentially large. So this exponentially large density of states at the bottom is pretty much tells you that the Boltzmann picture cannot work. Because in the Boltzmann picture, you describe the many-body states as configurations of quasi-particles. Well, the number of quasi-particles is n, and their energy is about 1 over n. So you don't have enough states with energies of order e to the minus n by just using quasi-particles of order n, of energy of order n, and degeneracy and total number of quasi-particles being n. So there's just no way that you can write this many states at such low energies using quasi-particles. And so in this model, this exponentially large degeneracy is telling you that really you have very complicated wave functions. In the Boltzmann theory, if you have a quantum state, the ground state, and you want to create an excitation, what you do is just to move a particle from here to there. So the excitation wave function is almost the same as the excitation as the wave function of the ground state. But here, every state is totally different. there is many body entangled in some very strongly chaotic way. All right, you can also look at dynamical properties like a Green's function. Won't go into the detail, but what you then find is that all the dynamical spectral functions have a width, which is precisely given by this Planckian time. So that's also very encouraging, because in the experiments without quasi-particles, you observe Planckian time in many properties. So, and it's really, quite remarkable when you think about it, that a dissipative property could be completely independent of the rate of collisions that you would estimate from a Boltzmann-like picture, which would be of, by Fermi's golden rule, be proportional to u squared. Okay, all right. So that's a description of the SYK model with a little interruption. So now let's take this toy model, which is, I think, taught us a lot in the last few years about the nature of many-body system without particle-like excitations. Let's take this model and see what it can teach us about other systems. So one system it has taught us a lot about, but it turns out quite remarkably to be much more than a toy model, are black holes. So let me just introduce black holes a little bit. You don't need to know much. I don't know very much, but well, we'll see. Okay, so black holes are solutions of Einstein's equation, which were discovered by Schwarzschild first, when he pointed out that if you solve the vacuum Einstein's equation, there were these black hole solutions which had a horizon of radius r, and nothing in the horizon could ever escape because of the curvature of space. Inside the horizon could ever escape because of the curvature of space-time. In particular, for the Earth's mass, the horizon radius is 9 millimeters. So this is really a very, very dense object. What's even denser than this number would suggest, because actually Einstein's equation says these are vacuum Einstein's equation. At the horizon, there's no matter. That the matter would completely collapse to a singularity at the center of the black hole. So classically, there's a singularity, and all the matter is at that one point, which naturally raised a lot of skepticism whether such a thing could ever exist. But it certainly does. But then what do we do about the singularity? Well, it's clear that to really understand what's going on there, which I don't think anybody does even today, you should apply quantum theory to it. Okay. But undaunted by these issues, Stephen Hawking in particular made an amazing step forward in understanding the effects of quantum mechanics on black holes. And we can think about that in terms of this EPR experiment. So imagine I do this EPR experiment by separating two entangled particles across the horizon of a black hole. So they're still entangled by the rules of quantum mechanics because there's really nothing here. This is still empty space. So they can't disturb these spins. And so if one is down, the other is up, and vice versa. But now the important point is that to someone outside the black hole horizon, this other qubit is completely inaccessible. There's nothing, no signal or anything that can happen here that will ever enable the person outside the black hole to understand what's happening to this particular qubit. So as far as someone outside the black hole is concerned, holding the qubit, you have a random qubit. And I just told you in the beginning, randomness is entropy and temperature. And therefore, this is one way of understanding Hawking's result that black holes have both an entropy and a temperature. I guess Bekenstein had also said that, but Hawking actually computed the numbers. And so these are Hawking's famous results. The black holes have a certain temperature given by this expression for a Schwarzschild black hole, and an entropy proportional to the area. Another curious fact is that if you take what's called the ring down time of black hole, if you had two black holes merging, there's a certain ring down time. This is what it is in Einstein's equation. You combine that with Hawking's equation and you get the Planckian time. So black holes are systems which, this really was the first hint to me personally, that black holes have something to do with non-quasi-particle dynamics, because these are both systems that appear to relax to equilibrium in this Planckian time. Okay, so let me say a little bit, not too many details, but at least the principle of what Hawking computed. And it's, in the end, once you understand what he did, it's not that complicated a calculation. So the Feynman prescription is, if you want to compute the partition function of any quantum system, you take its classical action and then integrate over all possible configurations. And you do this in Euclidean time, where the circumference along the time direction is h bar over kVt. Okay, so if you do that for the Einstein theory, and I'm going to do it actually only for theories that also there's a net charge Q at the center of the black hole. So if you do it for the Einstein-Maxwell theory, and also for the Einstein theory for that matter, the geometry of the black hole has a cigar geometry. So here's the horizon, and in imaginary time, space-time just ends. And so you're really always outside the black hole. And where h bar appears is in the circumference around in this direction. So this is the radial direction, this is the time direction, and the angular direction is not shown in this picture. Okay, so you take this is the saddle point of this action. And what Gibbons and Hawking said, well, let's just evaluate this action by a saddle point and not worry about all the other corrections. So if you just evaluate it, you do get the result. This is the Hawking result. And if you use Einstein's equations to convert this to what happens at low temperature, then this is the final result. It's something that depends on the area of the black hole at 0 temperature, which is related to the charge of the black hole. And then there's a constant plus a term linear in temperature. Okay. So where else have we met an expression for entropy which is constant plus linear in temperature? Well, that's exactly the SYK model. And these are also models which have this Planckian time dissipation, and there are several other similarities, which I noted all the way back in 2010, suggesting there's a close connection between the thermodynamic properties of the black hole, of the charged black hole, and the SYK model. But today we know that it is actually a very precise connection, and let me show you why. Okay, let's see. So this I've already mentioned, I guess. Hawking obtained the black hole entropy by computing everything outside of the black hole. And this allowed Hawking to avoid the contradiction associated with the singularity at the center of the black hole. And so, but then this really raises a question, there's no Hamiltonian here. All the entropy is presumably due to degrees of freedom inside the black hole. We don't know anything about them, but somehow, amazingly, we can still compute the entropy. So is there a quantum system whose density of quantum states, as demanded by Boltzmann, is in accord with the computation of Bekenstein and Hawking? All right, so I'll show you how we can at least find an example of a quantum system which has exactly the same generic density of states you would find for a non-supersymmetric charged black hole. Okay, so the key feature that allows us to make this connection is a very special property of charged black holes, which is a property of dimensional reduction. So here's a charged black hole, and say you're falling into it along the direction, radial direction zeta, and you're solving Schrodinger's equation as you fall along, then you'll find that as you approach the horizon of the black hole, you can completely ignore the angular direction. Basically, you can just work in the S wave approximation. So in the S wave approximation, you're living then in a one-dimensional space and time. So you can just solve Schrodinger's equation for quantum gravity in two-dimensional space-time. Furthermore, the metric of a charged black hole in this near horizon region, the two-dimensional space-time, turns out to be ADS2. So this is a space-time with a lot of symmetries, and that allows one to really completely solve quantum gravity with this near horizon geometry. So I won't go through any of the steps, but this is what you find. You start with Einstein gravity in 3+1 dimension near a charged black hole. You take its low energy limit. You get an overall factor, which is the Hawking entropy at 0 temperature. And then you get a theory of quantum gravity in 1+1 dimensions. And this is what's now called JT gravity. It's not just purely ADS2, there's a certain boundary condition that you have to worry about, which comes very naturally when you reduce it from this higher dimensional theory. And amazingly, this two-dimensional gravity theory, you can further fix the gauge of it and make it a theory only on the boundary, because there's no real dynamical excitations in gravity in 2 dimensions. And you get some action, which is now in 1 dimension on the boundary. And what is that action? Well, that action turns out to be exactly the action that we got for the SYK model and many other similar 0+1 dimensional quantum systems. Okay, so that's, this seemed, the way I presented it, this is some amazing coincidence. But once you examine the symmetries of ADS2 and the symmetries of the path integral of the SYK model, they're essentially the same. They have this SL2R symmetry, and that ultimately is what's responsible for this remarkable connection. So this tells me I can now just take the previous results for the SYK model and apply them to a black hole. So the leading Hawking result was the entropy was a constant plus a term linear in temperature. And we had learned that the correction from the SYK model was -3/2 log T. Well, so that should also be here. This is the Hawking result, and there's a -3/2 log sort of 1/temperature. And so this is, and it comes for the same kind of quantum gravity path integral that you meet in both problems. Okay. There's also a term that's independent of temperature, which is much more subtle to calculate, and was only obtained correctly recently by Ilyasova, Murthy, and Turiachi, and sort of analogous to the log n term for the SYK model. Anyway, so if you put all this together, you can convert the entropy back to a density of states, because we know how to convert this entropy back to a density of states from the SYK model, where we had a bona fide quantum system with some energy levels with exactly that dense entropy. And so this is the answer now, which was only obtained recently, for the density of states of a generic charged black hole at low energy. This is the Hawking answer, the exponential factor. Then you have the cinch of the square root of energy, which was obtained by Kotler et al. And now we can apply it to this generic black hole. And there's a free factor here, which independent of energy, which depends specifically on the nature of the theory of our universe, how many massless fields you have, and so on. It's not something you can get from the SYK model. Okay, so but the general feature you note now is that there is some quantum system, some strongly interacting quantum system, which has the requisite energy dependent density of states. In the SYK model, these densities, the precise energy levels are extremely chaotic. But if you coarse grain a little bit, in fact, coarse grain over an energy range, which is e to the minus n, or in this case of order e to the -1/g, e to the minus this number, then it's a smooth function, and so that tells you that it's highly self-averaging, unless you look at the energy scale of order e to the minus a0 over g. Okay, and there's and the fact that there's a 0 temperature entropy is not related to any degeneracy. And in this context, it's perhaps worth mentioning that Oh, so this is the Bekenstein-Hawking result. This is obtained from the SYK model, and that was obtained by Eliasu, Murthy, and Turiachi. So it's worth noting that there is another system where people have computed microscopically the density of states for a black hole. And that's in supersymmetric string theory. But there, in fact, you find a delta function with a coefficient given by the Hawking expression. And there is a degeneracy, and that's highly non-generic. It's a consequence of supersymmetry. As shown in these papers, there's also a small gap, which is also highly non-generic. The generic behavior is really here without supersymmetry, low energy supersymmetry. And so this has given us, some new insights into how to think about the quantum theory of black holes, at least charged black holes at low energy. There's been a lot of work recently on things called page curves and wormholes, which I won't say anything about, which builds on this understanding of what's happening to the density of states of these black holes. Okay, so to conclude this part, yes, I have over 10 minutes, so maybe 15 minutes left because there was a 5-minute break. So one way you can say this in modern language is that, there's an SYK model at center of a black hole. Well, not quite, but it's a simulation. It's a quantum simulation, which shows that the Hawking result makes complete sense. In this, at least in the sense that the density of quantum states matches the gravitational entropy that was computed from the outside of the black hole. And there's been many other investigations looking at many other properties, and a lot of progress has been made in that direction. Okay, so finally, to close the circle in the remaining 10-15 minutes, how about strange metals? So I didn't care about black holes in '92, and it was strange metals that really led me to think about this particular model. Do we understand something further about strange metals from the SYK model? So this has really been, again, a subject of great activity in the last, 5-10 years, maybe, and even longer in some sense, starting from the SYK model and trying to build up some understanding of a realistic strange metal. And I'll tell you about some relatively recent ideas where I think we are pretty close to the answer, but that's maybe a personal opinion. Okay, and so this recent work is done in collaboration with Avishkar Patel, who's a postdoc at Flatiron, current student Hayu Guo, and a current postdoc, Ilya Astles, who's on his way to Wisconsin. All right, so getting deep into solid state physics now. What is a strange metal? Well, I told you about linear resistivity, but a lot else is known. The specific heat in almost all strange metal goes as T log T. The optical conductivity has this form where the transport rate is either linear in frequency or linear in temperature. And similarly, the self energy of the electrons measured in photoemission is close to linear in frequency or linear in temperature. So, okay, so these are all measured properties from experiments that we'd like to get in one consistent theory, and I'm going to present one such theory in the remaining time. So to obtain this theory, it turns out the correct step is not to generalize the SYK model, which a lot of us were working on and trying to do in the past, but to generalize to what's now called the Yukawa SYK model. So the Yukawa SYK model is very much like the SYK model, except it involves a boson and a fermion. So you take some fermions, maybe you have no dispersion at all, and some oscillators phi, and you couple them together. Now you can have the Yukawa coupling. And just like in the SYK model, you take this coupling constant and make it a random function of its indices. So this model can be solved, and there's been a lot of work on such model in the last few years. And it has essentially all the properties I mentioned of the SYK model. You know, the zero temperature entropy, the time parameterization mode, the same sinh square root of E energy. Okay. So this is a model with no spatial structure. Again, bosons and fermions all interacting with each other. It's essential that you put in some idea of space because we want to describe a strange metal, which is not at one point, but extended over, say, two-dimensional space. So what happens when you have fermions moving, or metals, fermions moving in space, you get a Fermi surface. So we example, you get a Fermi surface occupied of states here. Then what is the boson? Well, we imagine, for example, that there's some phase transition where this Fermi surface distorts either in this way or that way. So then you can introduce a scalar field, which is positive when you're in this shape and negative when you're in this shape. And when this symmetry breaking happens, there's an onset of the expectation value of the scalar field. So this scalar field is an example of the field that will serve for a boson. Okay, so we want to write down, and then we expect that at finite temperature, this quantum near the quantum critical point, perhaps there's a strange metal here. Okay, and is there one? So in the remaining few minutes, I'll give you the conditions under which, where near such quantum critical points and many other similar systems, you do get a strange metal. Okay, in this cuprate phase diagram I showed you earlier, they may well be such a critical point, or they could be more complicated phase transitions involving Higgs fields, and the Higgs field can also take the place of phi. All right, so this is, I want to write down some semi-realistic theory of this kind of phase transition of coupled fermions and bosons. So as I said, you take the fermions and have them occupy a Fermi surface. You put in some some interaction between the fermions. And there could be various form factors here that I've omitted. But I want to write this interaction using a boson. So I decouple this interaction by this boson phi, because when you integrate over phi, you will get back this interaction. Here, psi dagger psi represents some order parameter, not just the density. There's form factors that I've omitted. All right, so here's a theory you would like to solve. A scalar coupled to psi dagger psi in the presence of a Fermi surface. So the last 25 years, I've seen a lot of work on such theories, and I think we roughly understand what they do. In two spatial dimensions, the basic answer was already obtained by Patrick Lee in '89. And you find that the Green's function is written in this form where the self energy is very large. And in the Boltzmann term, this tells you that the scattering time is extremely short and there are no quasi-particle excitations. So you have a system that has no quasi-particle excitations. Does it look anything like the experimental observations? And the short answer is no. If you try to compute the conductivity, it doesn't look like that of a strange metal, or in fact looks like a perfect metal. So although the electrons are scattering so strongly that quasi-particles don't exist, that doesn't mean that the current is degraded. You still have some center of mass motion of the collective fluid of electrons and bosons that flows without any trouble. So in fact, the conductivity is essentially perfect. This strange omega to the minus 2/3 term that you appeared in the self-energy doesn't appear in the conductivity, even though that was claimed for quite a while. Okay, so you can just give up, or you can say, well, we've got to stop this perfect metal. You've got to put in some impurities. So the natural thing would be to put in some random scattering, V of R. And if you look at this and solve this, you find, again, that doesn't work. That just looks like a dirty Fermi liquid, even though there are no quasi-particles, and as far as the transport properties are concerned. So what is the key to getting a strange metal? Well, the key is the following. which becomes apparent when you look at some experiments. So if you take a high temperature superconductor and look at it at a micro scale, say in scanning tunneling microscopy, so this is some measurements of some kind of local gap scale in a superconductor. And you find that the local gap is very broadly distributed. Its width is almost equal to its mean. And there's lots of local scale disorder. And to us, this means that the interactions are what's random, not just the potential felt by the electrons. It's the interaction between the electrons that are strongly random. So really what you have to do is you take this interaction J and add to it a term that's random in space. And now by rescaling phi, I can put that interaction in the Yukawa coupling. So you have to take fermions and bosons moving in 2 dimensions. And the most important part is this G prime. With the Yukawa coupling, that should be a random function of space. Okay. All right, so this is the finite dimensional generalization of the Yukawa SYK model. And we can solve it by very similar methods, which I haven't described. And when you solve it, you get, amazingly, exactly what you need. So if you compute the conductivity, it has exactly the form that experiments show, with a transport rate that's linear in frequency and temperature. But notice the coefficient here is G prime squared. And the self energy of the electron also has a term linear in frequency, but this linear in frequency depends both on G and G prime. So both on the random interaction and the non-random interaction, whereas the transport only comes from the random interaction. So that's, we claim, are the key ingredient here, that spatially random interactions in a Yukawa SYK model can quite universally explain all the very universal strange metal phenomena. Okay. So that's the end of my talk. So the summary is right here. So the SYK model is a solvable toy model without particle-like excitations, exhibiting thermalization and many-body chaos in this Planckian time. And remarkably, this thermalization time is independent of any microscopic energy scale. So this is really a toy model, but the toy model captures and has a lot of insight into the universal low energy quantum dynamics of charged black holes, where we see that there is at least one Hamiltonian, or a whole class of Hamiltonians, which has discrete energy levels, and a little bit of co-squaring over the energy levels gives you exactly the Hawking result for the entropy. And corrections to it. And finally, the famous properties of strange metals, including linear to resistivity, T-log specific heat, 1 over omega optical conductivity, and marginal Fermi liquid electron spectrum, all arise from a Yukawa SYK model with spatially random interactions in 2 dimensions. Okay, and that's our recent result. I can also summarize this other picture here. So we've talked about a model of multi-particle entanglement in one set of variables, which is size and phis. It's led to some understanding, I believe, of the strange electrical properties of something like YBCO, and a dual set of variables. And in fact, in the SYK model, you can perform the duality exactly. The dual set of variables are the time reprimerizations, which then map onto quantum gravity fluctuations outside a black hole. It describes many interesting things about charged black holes. So thank you.
Thank you very much for very interesting talk. So now let's have a Q&A session. So for on-site audience, please raise your hand. And for online participants, please write your name in the chat box. Do you have any?
Yeah, maybe. I shall start. Yeah, thanks for very inspiring talk. So I realized that, yeah, in your discussion of density of states, so in large system, there are exponentially large number of states, which means that at least if you look at the middle of the spectrum, then exponentially small energy energy spacing is kind of natural.
Yes.
But
yes.
if you go to low energy, then yeah, as you pointed out, if the quasi-particle picture is valid, then the level spacing should be not like exponential, but the power or small.
Yes.
So yeah, I perfectly agree. But then, in some sense, this SYK type behavior is in some sense natural because it's a generic behavior in the middle of spectrum that the level spacing is so small. But my question is, in this view, in ordinary systems like ordinary metal and antiferromagnet and so on, there are so many body systems which has quasi-particle like description that is in some sense it looks rather mysterious. Of course, if we accept random type picture or we can understand, but I just realized that this quasi-particle description, which is valid for so many systems, is in some sense miraculous from this.
Well, yeah, so one point I should make, which will perhaps clarify, getting a extensive zero temperature entropy, which the SYK model, is a sufficient condition to not have quasi-particles, but it's not a necessary condition. That is, in this case, there is no spatial dimensionality, and therefore the density of states is extremely large, down to zero energy. But if I take like a conformal field theory, suppose I take a 2+1 dimensional Ising model, that and I put it on a sphere, as we were discussing earlier. That also, as far as we know, has no quasi-particles, although no one's proven it. Someday somebody might find a dual description which has a quasi-particle description, but as far as we know, it doesn't. But it doesn't have a finite zero temperature entropy. And the reason is that in finite dimensions, at least if you take the black hole point of view, there's something called the Hawking-Page transition. So below the Hawking-Page transition, you just have low density of states, and above it, you have this exponentially large density of states. So what's special about the SYK model and what makes it much easier to work with is that the Hawking-Page transition already happens at zero temperature. You don't need to, it's always a black hole. But most other systems, you have to go above a certain energy before you see the exponentially large density of states. Yeah, okay. But so here we're just using it to our advantage. If you have no spatial extent, then you can prove that there is no, it's provably chaotic, there is no quasi-particle decomposition, which is not an easy thing to prove in general.
So in generic system with quasi-particle low energy description, there is something like a Hawking-Page transition at certain.
Yeah, well, certainly in the larger limit, there's a transition, a sharp transition, but for finite end, it may just be a rapid crossover of some type. Yeah, I don't think it's understood in detail what would happen at finite end. Yeah. So if I take, say, for example, a 2+1 dimensional Ising model, and then go to very high dimension operators, dimension h going to infinity. Eventually, the density of these operators becomes exponentially large, so e to the h to some power. But exactly how it reaches there, I think that's an interesting open question.
Thank you very much.
Thank you very much. Is there any? Please.
So SYK model is a model with a disorder.
Yes.
And then that raises an interesting question about the holography. There's ensemble average and holography wormholes and all that. So but some people don't like the idea and then try to mimic it by model with this without disorder. And as you know, like Wittgengrau model and things like that, they try to, I think they, if I'm correct, they reproduce the correct behavior at the leading order. But now you have more data like sub-reading corrections and things like that. So can you imitate this? The question is, can you imitate your discussion with the model without disorder? Is it possible?
Yes. Okay, but much harder. I mean, I think
I see.
that's my understanding, and and consistent. I think many things I've heard, say, for example, Steve Schenker say. So the reason for introducing disorder, even for us initially, was it's amazingly when you introduce disorder, life becomes simple.
Mm-hmm.
You can solve certain things once you average, because it very easily gets you around the difficulty of knowing every energy level. I don't know every energy level. I don't even want to know every energy level. So why don't I take the couplings random? So I only focus on the self-averaging quantities. So in principle, I would, guess if I could really solve, super Yang-Mills at large N and get every energy level, which is an impossible task, that I will get all of these properties. But yeah.
Oh, I see.
I mean,
okay. Yeah, so sometimes people speculate that there is a macroscopic description, which is a full description, but there is also coarse grain description involving this.
Right. Yeah. So we're only interested in the coarse grain description.
I see.
And the point is that but I do believe that the coarse grain description of a random system, a non-random chaotic system, or a random chaotic system are pretty much the same. So why not work with a random one, because it's easier to get the coarse grain description.
I see. Great. Thank you.
Thank you very much. Do you have any other?
I mean, in
questions?
one body quantum mechanics, that's a well-accepted trick. If you take, for example, a single particle in a billiard, and you want to look at its energy level, they are extremely chaotic. So yeah, I cannot predict every energy level of single particle in a billiard. But if I want to know something about the statistics of the levels and their distribution and their 3 or 4 particle correlation function, I can get those exactly by doing random matrix theory. So there again, yeah, as an example of how you can model completely non-random system, a particle in a billiard with a random matrix. Here, in some sense, we're much better off because the levels are so dense. It's not as if the levels are spacing out of 1. The levels are so dense, exponentially dense. It's very natural to just do this, and you don't have to coarse grain very much at all. You only have to coarse grain over energy width of e to the minus n, e to the minus a over g, e to the minus the Hawking entropy, which is a very small effect. Yeah, but nevertheless, I guess if you've heard about the form factor, they're looking at very long time. Even at that energy scale, you can get statistical properties which are believed to be generic, but not proven. Yes.
Thank you very much. Do you have any other comments or questions? Can I ask one question?
Yes, please.
Sorry. Actually, I'm not serious, but it's experimental guy, and I have learned that randomness can induce very interesting bulk phenomena like T-linear resistivity or something. So I agree that, and I'm a neutron scatterer, so I'm always using big sample.
Yes.
Then I think coarse grain method should work for big sample. But nowadays people are, focusing on tiny systems like graphene or microfabricated samples.
Yeah.
So do you have any comments on applicability of your theory? What kind of size scale?
Yeah. Well, so unlike black holes, where randomness was a convenience, the message of the last part of my talk, especially this one, that random is essential to understand the linear T resistivity. It's really, you need it to relax momentum in just the right way with the interrandom interaction, so you get a linear T resistivity. Right. So, then I showed the graphene data, which had a linear resistivity, and you would think graphene is very clean. Well, that was twisted bilayer graphene, and by all accounts, it has quite a bit of disorder. Now, there's been a recent experiment by Andrea Young on untwisted graphene, multi-layer graphene, where he has all the exotic phases, and there he doesn't see a strange metal. So we do have a prediction that as you make your crystals cleaner and cleaner, the strange metal behavior will disappear. Let's see, maybe we'll be proven wrong, but that's what we're predicting. Now, but something like neutron scattering, when you're measuring the electron spectrum, but not transport, then disorders are just a nuisance. You don't really need it. You don't want disorder. You want just a big signal, because it's just going to broaden your spectral functions. Yeah. So right. So it has two faces, but for transport properties and strange metal behavior as measured in transport, we're very confident that you won't get it without impurities. And so that's a statement that can be proven wrong by future experiments. But so far as I know, it has not.
Thank you very much. So, is there any comments from online audience? No? So, okay, it's time. So let's thank Professor Sashev again. Thank you very much for nice talk. Okay, let's close this colloquium. Thank you very much for your attendance.